Hello everyone, welcome to this video on data science for class 12 CBSE. This is our video number 2 where we'll be reviewing some of the uh, statistics concepts that many of you will already be comfortable, like mean, median, mode, range. Some of that, like IQR, variance, standard deviation, correlation. We'll take some example and explain so that you get a fresh look at it, and then we'll focus on some of these Z score, one of the very common distribution that is called normal distribution, and we'll talk about couple of t-test and hypothesis testing, which is kind of testing one or the other way in your class 12 syllabus, and eventually we'll end this video with a basic simple introduction of central limit theorem. So let's get started. Mean when you are having um, large data set, mean can help you give some idea, right? What how the data looks like. So say if you are having hundreds of numbers, and if you want to make some sense of it, right? Mean is something that gives you that average, sort of idea where the average is, right? Typically, in a well distributed data set, uh, you can expect that half of the numbers uh, should be lower than the mean, half of the numbers to be higher than the mean. But as you see, there is a term outlier, and which is covered in your course in several ways. Uh, so if there are outliers, like only some of the numbers are very big, either on positive or negative side, they can influence the mean in a way where it will not be very representative of the overall data set. So we'll actually keep talking about it. But as you know, to find out mean, what you do, simply sum that number and divide by the total numbers that you have, right? So in this particular case, you sum of the four number and divide by the total, so you get actually an average. And as you might see in this case, less than 7 are 4 and 6, more than 7 are 8 and 10. So 7 gives you some idea how your overall data set is, but there could be extremes. We'll talk about that. Median, on the other hand, right, is kind of more orderly than mean, because it doesn't depends on any of the extreme, and as long as your data set is sort of uh, roughly uh, distributed, median could give you a better indication than uh, you know uh, mean, right? And as you know, in case of median, what you typically, how you find it is, if there are odd numbers of data points, it will be your midpoint, right? If there are even number of data points, it will be average of your midpoints, right? So in case if there are very big positive or very big just few negative number, your overall representation is very close to the median. Um, of course, actually, median is also having its own set of issues. So if you have half of the numbers which are very different than another half, maybe your median uh, will not be that well represented. Mode is another important that typically talk about the most frequent data point, right? And the way you find is uh, the one number with highest frequency, right? And as you know, if you don't have one number, then you choose the one with which is equal to the the next most frequent number. That's how you find it. So mean, median, mode, you might be very comfortable. You can just like a review, and one distinction that I would like you to kind of keep in mind is median is sort of more robust, in case of outlier cases, mean sort of somehow is skewed towards the outliers because they kind of have larger weight of it. Now, we'll see some of these range-related and interquartile range-related details. As you know, range is something that talks about the spread of your data set, right? And the way you find it is find the maximum, find the minimum, and then take the difference of that, right? So in a way, it talks about in the overall spread from where to where your data points are. Your interquartile range, right, is something where you uh, take the difference of uh, third quartile from the first quartile, right? And we'll talk about how you compute, this individual uh, quartile, right? So, as you know, quartile is 20, 20, fifth or one fourth of it. So you have Q1, Q2, Q3, right? Q4, and the way you find quartiles is you sort the number, right? And you know uh, basically if you take the median, right, of the lower half of the data, so that's the 25th percentile. If you take median of the upper half of the data, that is 75th percentile. And then you can use a very simple formula of Q3 minus Q1 to get your IQR, right? Some of these could be important because at least one or two of your previous questions paper, right? This has been touched upon. So yeah, I mean, it's a this is the five-step process, right? So basically, if your numbers are, as you see in this example, the first step that you do is solve this, right? Then you find the median of uh, you know Q1. You will find the median of Q3, right? And then you subtract. So in this particular case, if you see, uh, since there are even number of data points, so after sorting, 9 and 10 are two middle numbers. So you have got your median as 9.5, and anything lower than 9.5, that is up to 3, 5, 7, 9 in your lower half, and then all the numbers greater than 9, that is 10 till 20, right? 10, 12, 15, 18, 20, those are your upper half. And Q1 is going to be the median of uh, you know uh, the first quarter, right? So in this case it is 7. In the similar way, Q3 is median of the third quartile, and that is 15. And as you know, IQR you can get it simply by subtracting Q3 from Q1, right? So it's simple five-step process. We'll see actually once you review your question paper and see what are the variations that has been asked in past. But decile is one that has been actually tested several times, right? And like you look for quartile, right? You got a P25th, like Q1, Q2, Q3, Q4. Decile is 110, so there are 10, right? Q1 till Q9, or we call it D1 till D9, right? D means decile. So decile 1, decile 2, that way to decile 9. And this is actually about talking about 10% of the data is decile, right? There is a very simple formula for it, right? So if you have n data point, you add one, so that is n plus one, and then actually if you are looking for position of say any of the kth one, that is from 1 to 9, then you divide 10 to that kth terms, right? To k by 10 into n plus 1. And so if you are computing D1, it will be 1 by 10 into n plus 1. If you are doing, say D9, it will be 9 by 10 into n plus 1. So basically, the way it helps you is basically find the start, right, of the base quartile, base decile, and then from there on you extrapolate to the next one, right? And you'll see a formula for doing that. Um, so you will take the same example, as in last example, as in last case of IQR. So the first step is sort it out, which means that arrange your data points in increasing number. And then if you want to compute D1, it will be 1 by 10 into, since you are having 10 overall number here, so 10 plus 1, right? If you had 20, it would have been 20% that way. So you got position of D1 as 1.1, and if you want to find out dk, this is going to be your position value at lower position, and then you take fractional part, and then you take the difference to the next value, right? So in this case, if you see lower or the first value is 3, the fractional part is zero point 0.1, right? This is going from 1.1 and subtracted with 1, right? And your difference to the next value is you are having actually 5 and 3, so that's up to 2, right? So your d1 here is simply calculated to 3.2. So you can actually repeat it to calculate any of the other designs, and we'll take a couple of examples once you start giving your actual questions that has been asked in past, right? Now uh, we talked about these q1, q2, q3, um, and so these will be your four things related with range, which will be actually range IQR, the size of quartiles, and you will see some of the numericals that have been tested in your question paper. What must be this there. Okay, so far we have just looked at some of the basic mean, median, mode, and range related variations. We move to another important term, which is standard deviation, right? And there are two related terms, variance and standard deviation. Uh, Variance is one that helps you understand your spread, right, over the data set. And how you do it, you get the mean value, right, of your data set or whatever sample that you are having, and then you subtract the mean from each individual data points and square it and then sum it up. So that's why you have this term, right, sum of xi minus us squared, and then you divide it by total sample size which is there in this case. So a standard deviation is just the square root of it, right? So the two important thing, the one that is mean, that was the average also, and variation, and it is square root, that is the standard deviation, known as sigma. So mu and sigma will be some of the very commonly used terms whenever you are looking at your data distribution. And it's very important to have some intuitive understanding about it, right? So just to repeat, your mean is something that you just get it by averaging your numbers that you have, and variance is averaging your differences, right? A square of a square some of your differences for mean, right? And the steps are again, yeah, if you have a data point, right, say for example in this case 37596 or whatever it is, you get your mean by simply summing it up and dividing by total numbers, and then you look at the square differences and sum them up, divide by your total number, right? So say in this case your variance is 4, standard deviation by square root of it, that will be 2. So this is the data set, but if you have to describe it, it will be having a mean which is 6, and standard deviation that is 2, right? So we'll have another look at what exactly and how exactly this standard deviation of 2 should be interpreted, and there is another term for it that we call Z score, right? So Z score is something that gives you some idea that how far away, right, how many standard deviation away your data point is from the mean of the distribution, right? And we'll see that for certain specific distribution, your one standard deviation, two standard deviation, and three standard deviation of your data sets almost capture more than 99% of overall data set that you are having. Right? So just to get it, how you get your Z score by subtracting mean of your individual mean from your individual data point and dividing it by standard deviation, right? So if you take again, so this simple, right? 55, 70, 80, 85, 90. Let us say that these are actually in a score of 5 yesterday in one of your tests, right? So you get the mean, which you just sum it up and divide by total sample size. So you got 76. Uh, you use the variance formula, which was squared, uh, you know, uh, sum of differences, and then dividing it by your sample size. So that is 154. And then you take the standard deviation by taking a square root of it, which is 12.41 in this case, right? So now if you pick that, how far from mean 80 is, right? So you subtract 80, mean from 80, that is 80 minus 76, and divide it by the standard deviation, which is 12.41 here. This comes like, 0.32, right? So you will start developing some intuition and say that, this particular number is so many standard deviation away from me. 0.32 you can say less than half a standard deviation away. Uh, at some stage you'll start having some idea about, when you say 1 standard deviation away, 2 standard deviation away, 3 standard deviation away, because outlier is tested in with couple of variations in your overall syllabus, right? And one way of knowing outlier is how many standard deviation away given numbers are, right? So that you can treat them differently. For example, anything other than 3 standard deviation, right, or 2 standard deviation, you must simply drop them, when you are actually going for cleansing your data set or applying some of those standardization. So with this now we are set to actually kind of, talk about this term, distribution. I think one of your stat or probability courses, right? You might have looked at how you calculate probabilities, and then possibly have gone through terms that we call, probability distribution function (PDF) or cumulative distribution function, that is CDF, right? One of that. So this is, we'll just basically give a very brief intro, right? About the two type of distributions that we have, that is discrete and continuous. But before we actually, put a specific details out there, right? The idea of distribution is, right, that whatever data set that you are having, how individual values are spread out, right? So that's why we have been talking about mean, median, mode, then standard deviation, then some of the other either IQR or decile related changes, to make some sense of how individual data points are, and their distribution with whatever frequency that is present in your data set, right? Uh, is actually having some typical characteristics, and they are known by some more common ones. So we'll actually see one of that it is shown. But before we go there, uh, you know, uh, discrete distribution will one that will deal with distinct separate values, right? While continuous is one which will be actually talking about value within a range, right? So any value within a range, right? So this will be important. For example, we're looking for something like height, weight, mass score, right? So those will go into this distribution definition. While we are looking for some unbounded things like number of something or those, that will be a discrete one. More important here, when we are actually talking about, right, is how you define any of these distributions. So there are basically three things, right? One is central tendency, and as you know about central tendencies, those are measured through mean, median, and mode, right? So uh, how these mean, medians, and modes are, they are the same, different, right? Uh, Different from each other, how far, right? So and in many cases you might be just looking at for some of the popular ones, for example, your normal distribution, you expect mean, median, and mode to be the same, right? And then the spread, so couple of measures that will be range, variance, and standard deviation. So that tells you the spread of individual data point from the central means. So for example, either mean or typically mean, you can use others. And then actually, what kind of shape it is, right? Or is it actually kind of symmetric across mean or the central tendency measure, or skewed, or kind of well set, right? So that these three together gives you certain kind of characteristics, and there are some well-known distribution with very well-defined characteristics, right? And one that is actually sort of very very important for me is normal distribution, right? In this case, if you see, this basically, you are talking about continuous probability distribution, right? That is symmetric around the mean, right? And it forms a bell-shaped curve, right? You could correlate it, with, the way your individual marks are in a given class, right? So if you can look at number of people getting, certain specific marks and try and put it in a graph, right? You'll typically get a bell-shaped graph, right? But very few people will be having very high marks, 99, 98, or 100 out of 100, and very few will be having zero, right? Or 0 to 10 or 20 or 30. So if you say that passing marks is 40, so maybe 0 to 30 there will be very few. From 40 till 80, maybe there will be a lot of people, and 80 onwards again there will be just few people. So you know uh, if you see this frequency, and if you look at across mean, assuming that mean is 50 out of 100, right? So that shape is actually bell curve. You could have seen it, and we'll see it in the next pair, I think, right? So if you see the way we looked at, right, across central tendencies, uh, then spread and shape, right? In this particular case, your mean, median, and mode should be equal for normal distribution. As far as the spread is considered, uh, from mean, one standard deviation away on each side, that is 34%, and 60% overall. So your overall data point will be 68 percent. So if you are having 100 data points, 68 will be just as one standard deviation away from mean. Your 95 will be just as 95% will be just two standard deviation away from mean, and almost likely everything which is 99.7% or more than 99, right, within three standard deviation. And that's why you can see, right, one very simple definition of an outlier will be all the numbers which are more than three standard deviation away, right? So we'll keep coming to this outlier because this will be one of the important tool, and there are several other concepts that are repeatedly being tested in the exam. So the bell curve, that we are talking about, you can see, right, it is symmetrical and centered at the mean, and then on either extreme, there is a very thin tail, right? Okay, so we'll talk about another important, topic, which is correlation. And correlation again is very very important, uh, as one of the common basic concept that will be and variation thereof that will be using, not only in this data science course, but if you choose to study, right, and take you know uh, your next courses, or you will try and graduate in data science or some of the variation. Correlation is something that so far what we have talked about. We have talked about mean, median, mode. That talks about you know uh, the central tendency part. Then we talk about the spread, that was spread deviation variance, or range, or some other variations around that. And then we talked about the shape. We are looking at the data point. Now, you know when you are looking at you know um, any of the data set that you are having, right? So you could have large data set, right? And you have captured its behavior across several, characteristics that we call feature, right? So, you know, um, say for example, right, when you are talking about students in your class, right, and you are looking at their score uh, in exam uh, 10 versus their score in exam 11, or you can take some variation of it, right? then you expect that typically whoever scored higher in high school and typically score higher in 11 at most of the time. Those who have scored poor, they will score poor. Right? So correlation is something that when you don't know much about your different features, you just look at the numbers and see how they move relative to each other. Right? So uh, if it is a perfect positive relationship, uh, then correlation is something. So correlation is between 0 and 1, right? -1 and 1. So -1 is actually totally opposite behavior. +1 is perfectly in sync, and 0 is actually no relationship. So basically there is no linear relationship we are talking about, right? Linear is important here. Uh, so, for example, if you're talking about cricketers, right? So maybe if you look at their career history, total run made, and number of say centuries or 50s, there will be actually positive relationship. Those who have made higher number of overall run will be having higher number of say 50s or century. Similarly for bowlers, right, those who have taken a large number of overall wickets in their career, they will be actually typically having higher number of say 5 or 3 wickets in a given match or something like that, right? A very related topic with correlation is causation, and they're very confusing. And data point doesn't differentiate between the two. Causation is something when two things are happening just accidentally, right? For example, uh, uh, someone point this out that whenever it rains in Mumbai, right, certain Tendulkar scores a century. So if it is true, then as you know that raining in Mumbai and Sachin Tendulkar scoring a century is really not related. But it might be that when it rains, the situations there are favorable, and he goes and score well, right? There could be some other reason, right? Um, but it will never be that he if it rains he scores well, right? So that's how you have to start differentiating, between correlation and causation based on some idea about what the data points are, and this will be tested in many ways because there are several kind of spurious correlation which doesn't make much sense, and there are a lot of active research going on how to automatically find it out, because when we look about things in context, um, you can say it whether it is correlation or causation, but many a time when you are actually capturing your data set across very large features, and particularly when those features are not exactly known, or as a data scientist, where it's hard for you to kind of comprehend huge volume of data captured across large set of features. So in those senses, differentiating between correlation and causation, you do need many other kind of EDAs, that is explorative data analysis, and as a tool, uh, try and figure out from domain and other things. But keep in mind that um, correlation and causations are important, and we need to learn how to differentiate spurious correlation from the real correlation. One of the very well-known correlation measure is Pearson correlation, and it simply look at uh, the uh, differences, right, from mean for these two features or variables that we are talking about, and it is standardized by the standard deviation. So we'll not get into formula for that right now. We'll see that if it is captured in one of the question paper, we'll talk about that. Okay, so now let us move to jet test, right? There are several now key concepts that you might not have heard. Uh, uh, so jet score you might have computed, in your many of your math or stat related courses, basic stat related courses. You might have not, come across jet test or some of the other topics. But there is nothing to worry. We'll just actually talk about these, and uh, you know and when we look at and review your questions, we'll talk about it again so that you clearly understand and start using it to solve your papers well. So the basic idea behind J test is right, when we are going to do any kind of analysis, right? You only have data set which has been observed, right? So say for example, right, if you are looking at um, set of people, right, say who are watching on streaming devices like Netflix, and you want to make some kind of inference, right, about say average time or other engagement metrics, then there are actually billions of users across the globe, right? And even if you want to talk about a specific audience in a given geography, that could be several million or several hundred millions. And so you'll never get actually all the data points. We are going to talk about certain subsample of that, right? Or in many cases, your problem statement is like that, right? And so J test is the that basic test where uh, you mix you know no strong assumption, and the sample mean and population mean is assumed to be low, right? So we'll see actually some other tests where they don't need population mean. So those are very important. I mean, in this particular case, you can make assumptions that both the data sets are available to you, provided to you, right? In some of the other ways. So this is just a way of looking at uh, average behavior, right, across the two groups. And what J test tells you, right, is whether the sample mean that you are having is statistically significant or not, right? And in this particular case, if you see, some of the things that can help you answer is the average score of a class significantly different from the, say, national average, or whether two different groups, are performing differently on a test, right? So on assumption side, normal distributed, you know, so data is normally distributed, and you know how well when your data is normally distributed, right? We just talked about it, which means that your mean, median, and mode are same, and roughly 68, 95, and 99% of your data set are spread within 1, 2, and 3 standard deviation. And this also works on large sample size. So in this case, if you see, at least 30, right? Um, so basically, if you look at some of the step how you do, so it's improve, something that is called critical uh, test score, and that is actually compared using this formula, right? So you are looking at sample mean, which is x bar, and you are looking at population mean, you take that difference, and then you have a standardized your standard deviation by square root of your sample size, right? So in this particular case, now we'll actually talk about hypothesis testing, right? Let me quickly cover that, right? So hypothesis testing will definitely be kind of very new for many of you, at least some of you, right? Um, but this is kind of a procedure or a set of procedure or a method, right, which is used to test assumptions or claim about population based on sample data. So you just have access to some certain subset of your world data, and you are trying to make actually certain kind of whatever ideas or estimate that you are having. um, there is a term called null hypothesis, which is typically something that whatever experiments that you have in mind, you say that your null hypothesis, right, is something that contradicts it. For example, say if you are developing vaccine for some kind of viral disease, so you start with a null hypothesis saying that there is no effect of this vaccine on the viral infection we are going to talk about, right? And then you try and prove that your null hypothesis is incorrect, and you define your alternate hypothesis as yes, it is a very, very effective one, right? So the whole idea is, you set up your null hypothesis and prove that your null hypothesis is incorrect. And if you get it appropriate for your syllabus, there is just another term that we call p-values and significance, right? So typically most of the tests that you do is at 95% significance. Of course, some of them could be as high as 99 or even more. So, but typically if you're having a significance level at 95, then as long as your p-values are less than 0.05, which is 5%, that helps you make a decision whether you can reject the null or not, right? By doing two computations. One is actually, you collect your uh, critical test statistics, whatever is appropriate, and then compare it with the reference one, right? And if this one is greater or less, which is actually, indicated by your p-values, then you make a, choice of, whether you can reject the null or not. Just two more concepts, and if time permits or if your syllabus allows, we can actually talk. So there are actually, power test and also actually error one, type one and type two error, right? Which are primarily about, related with your. So what is happening if you reject your null correctly, right? uh, you have made the right decision, right? Think it this way. You can actually visualize more like, as a 2 by 2 matrix, right? So if I can actually, you know, um, say insert a table or just look at this, right? So reject uh, your H0, right? And this could be your correct decision, right? Um, but in some cases, right, you fail to reject H0, right? Fail to reject H0, right? So when you correctly reject H0, that is fine. When you fail to correctly reject H0, that leads to one of these type 1 and type 2 error. And we'll actually come and actually take a specific example if it is covered in your syllabus at some stage. But on just to extend it, if you are looking at comparing, right, means of two groups, uh, you know, uh, which actually in this case, if you know the population mean, and if you have taken a sample, and then if you want to make actually some inference about whether your sample mean is significantly different than population mean or not, assuming that population mean is known, one of the common test uses Z test, right? And yes, you set up your null hypothesis, right? Um, as you saw some earlier, then you set up an alternate hypothesis, and then you decide a significance level, especially for your problem. Um, Typically, 95% works well for very set of scenarios which talks about say a very big impact of any kind. You set her significance level at 99, or your significance here becomes actually you know 0.01. So we'll not go to two sample J test. We'll just talk about one sample because we don't want to add too many details which is not in your syllabus. And here actually for one sample J test, you find the critical value, uh, which in this case will be at 95%, 1.96, as you know, right? And in this particular case, if your computed Z is greater than this critical value, you can reject the null, which means that you'll accept the hypothesis that you started with, and otherwise you will not be able to uh, accept the null and you feel to reject the H. Right? So this is the process that we use. Before I go to the t-test, since I have covered the hypothesis one, we can take one example and see how we are doing it, right? So, say for example, in a school setup, uh, someone is hypothesizing that average class height is 160 centimeter, right? And there could be say 100 students or more, but you have taken a sample of just 36 of them, and their average height is 158 centimeter. Now, uh, as long as the standard deviation of population, is known, which is the overall class is known, at 5% significance level, let us say that we want to uh, decide, right? So, how you set up your null hypothesis? The average height is equal to 160 centimeter, right? Um, so in this particular case, your alternate hypothesis is going to be average height is not 160 centimeter, right? So in the first level we decided. The greatest statistics in this particular case is your you know sample mean is 158. Your class mean is 160 here, right? So you take that difference and your standard deviation was 5, your sample size was 36, so you're 5 by 6, and then your Z value is 2.4 and with a minus sign, right? So if you look at your normal distribution, right, uh, whenever you are having equal sign, you are talking about both side of the mean. So we call it two tail, right? Tail on the left, tail on the right. And for this two tail at 5% significance, uh, you'll be having critical value at 1.96. So since the absolute value of your test score is greater than this, you can reject the null hypothesis. And since you have rejected the null hypothesis, uh, you have enough evidence to say that average class student is not 160. So that's how you approach it. For many of these things, your sample average is anyway you can find out, but population, um, you know, uh, overall population, right? Mean and standard deviations will not be, available, and that's where t-test actually comes quite handy, right? And in this particular case, the only difference that you see is rather than sigma you are using s, which is just the sample mean, right? And the second works, pretty similar to check test, right? There is a history behind it. T-test is also known as a student test. This was actually, done by one of the famous statistician who was actually, kind of publishing many of his work with a pseudonym, a student test. Later it came to know the t-test. Another popular which I square, which will actually compare, multiple two distributions and so on and so forth. Uh, but yeah, I mean, this would be good enough for us when we have covered check test, t-test, taken one example, talked about one or two tail in brief, and also covered the hypothesis testing. We'll actually move towards closing this topic by touching upon another very very important you know term that is known as central limit theorem, CLT. Um, CLT is very very central to data science, one of the core concepts in statistics. Um, as you go across, right, you figure out that many a time you sample, right, and work on some small subsample of that for making variety of inferences that you are doing. And in that sense, whenever actually any of your models are having hard assumptions about distribution of data, it becomes difficult to uh, not violate that. That's where CLT comes very handy. And what it says that even if you know the your source distribution, your original distribution, if their population is not known, there are ways of actually kind of making it to one of the known distribution. And typically here what it says is if you repeatedly sample uh, from the uh, you know available data set that you have, the mean of those samples, right, uh, they will actually follow a normal distribution. So it's very important. Say you are having actually, uh, you are talking about, you know, you just have access to, like in your last case, right? You just have access to 36 subset of your data set. If you really want to actually kind of, uh, look at whether the 36 that you have, even if it is not normal distribution, if you start randomly choosing say 5 or 10 numbers in one go and take average of that, right? So then those averages will follow normal distribution. The basic answer is there is a term called IID, right? Uh, which means that identical and independent distribution. So as long as that is made, uh, you know, uh, this will be there that if you take many random samples from any population, no matter what the shape of population distribution is, and calculate the mean of each sample, the distribution of those samples means will follow a normal distribution, even if the population itself is not normal, have a mean equal to population mean, and have a standard deviation called the standard error, right? Which will be sigma by square root of n. So sigma is population deviation and n is your sample size. As you might have seen, right, higher the n, lower the standard error. So if you just have 100, your standard error will be 1/10 of your population standard deviation. So this is important because it deals away with any assumption on how your actual data distribution is. Uh, it works with large enough samples. If you take more than 30 samples, uh, your population could be of any shape, and for larger sample size it works well. Just to take one example, right? So if you just take say a fair die, right? So you know that your numbers are going to be 1, 2, 3, 4, 5, 6, either of that. So if you actually kind of say roll it 10 times and you take the average, right? And keep doing it for 100 times, right? So now earlier you would have just 1, 2, 3, 4, 5, 6. So if you had 100, the frequency of 1 coming, 2 coming, 3 coming, 4 coming, 5 coming, 6 coming, right? So you would have say in the typical case, if it was a fair die, you know uh, for 100 by 6, it will be actually kind of closer to 16, right? So the frequency would have been 16 for 1 till 6, right? So everything would have looked like a bar graph, right? 16 1, 16 2, 16 6. But if you actually roll it out 10 times, right, and take the average, then the number that you are getting, say 3.5, 5, 4.5, whatever the sample mean is, they will now be like a bell curve. So that's very important, right? And the number 30 is again many people get confused. What this is talking about is large enough sample, right? So that's why we are taking here 100 samples, right? So it's not that you need availability. Your sample size could be very small, right? Only thing you have to keep repeatedly sampling it and take the mean of those samples. So in this case, for your dice, what you are doing, you roll it 10 times, you might have got say 2 1 3 6, 2 2, right? Another few fours or something, and then you actually take those frequency, those occurrences together and take the average. So whatever number that is coming out of the 100, you get a normal distribution. uh, it actually simplifies and helps manage many of your assumptions needed for your this. So in this course so far, we have talked about many of these common concepts around mean median mode, variance, correlation, hypothesis testing, few others. Uh, yeah, we'll stop here. In the next class, we'll actually see a couple of questions that are being asked on these topics, and then we'll actually cover your next topic, which is regression. Uh, See you in your next video.